Hi everyone, welcome to my channel Tech Tutorials 2K21, and today we are going to learn about a spanning trees concept in design analysis of algorithms. So we'll start with the definition of a spanning tree and then we'll discuss what do you mean by a minimal spanning tree, and at the end of this lecture we are going to see how we are going to construct a minimal spanning tree with Kruskal's algorithm. So a spanning tree is nothing but it is a subgraph of a given undirected connected graph. So which include all the vertices of a graph. It should be connected without forming any cycles. So what do you mean by connected graph? So a graph is said to be connected if it's having n number of vertices, right? So then it must have greater than n minus 1 number of edges. So then only we can say that is a connected graph. So this condition will say like you can see if a graph is not connected, that is nothing but if graph is not connected, so then we cannot create any spanning trees for such type of graph. So you can have any number of spanning trees for a given graph. So now you can see, you can consider one example. This is an example of a spanning tree. So here you just forgot about all these weights on your edges. So now you can see here how many vertices we have? 4. So what we can say, when a graph is connected, it's having n minus 1 number of vertices, or it's having more than n minus 1 number of vertices. Now you can see here we have more than 3 edges here. Now we can see 1, 2, 3, 4, 5. So this is a connected graph. So now for the connected graph, whenever you are trying to construct a spanning tree, so what the spanning tree definition? It should connect all the vertices of a graph and without forming any cycle. Now these are different spanning trees existed for this example, right? You can consider this example. There are different spanning trees here you have. Now you can see A to D is connected, A to B is connected, and A to C is connected. This is a graph here. And then here you can see A to D and D to C and C to B is connected. So all of your vertices are connected here. And now you can see D to A to B and B to C. Now you can find this one. So you can also take like C to A and then A to D and then A to B. So now you can see this is a one graph, like C to A is connected, C to B and C to D is connected. And here it is another spanning tree. So because of that, we can say like for a given undirected graph, you can create any number of spanning trees. It's like this more than one spanning tree we can. And then what do you mean by a minimal spanning tree? So a spanning tree with a minimum cost is said to be a minimal spanning tree. So what do you mean by minimum cost? Now you can consider this same example. Now you can see here 4 vertices and here we have 5 edges, and each and every edge you are finding some value, and this is called weight. So what do you mean by a minimal spanning tree? Now you can construct a number of spanning trees for a given graph. So which spanning tree will consisting the minimum cost, and that spanning tree is said to be a minimal spanning tree. Now you can see in this example itself. So in design and analysis of algorithms, we have 2 different algorithms which supported to create a minimal spanning tree. One is Kruskal's and second one is a Prince. So we'll see here. See here, these are different possibilities of spanning trees which are constructed from this example, right? So in this example, and you can see that these are different spanning trees. Okay, and here you can see the cost of these spanning trees. Here the cost is 2 plus 2 and plus 1. So it is 5. And here the cost is 7. And here it is 10. And here it is 9. And here it is 8. Now you can see the minimum cost for this tree is, right, simply 5. Right, which is a minimum as compared to all other spanning trees constructed from this example. So we can say this is a minimal spanning tree. So now we'll discuss about the Kruskal's algorithm. So how the Kruskal algorithm is used to find out the minimal spanning tree for a given undirected graph. So this is an algorithm. It takes 5 different steps. What is the first step? You have to collect all the edges with the weights. So now each and every vertex is connected with an edge. So you have to collect all the edges. So in a given graph along with their weights, and arrange a list of edges in ascending order depends on their weight. So after we are collecting all the edges along with weights, so what we have to do, we have to arrange all those edges uh, in ascending order depends on their weight. And then the third step will say, like, we have to remove edge one by one from the list and add to a spanning tree. So if it forms any cycle, we have to reject that edge, and we have to repeat step 3 and 4 until no edges are in the list. So now consider this example. So we can see here 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices we have, and we have different edges like AB with weight 4, and AH with 8, and BH with weight 11, BC with 8 with weight 8. Like that, you have weights on these edges. So whenever you have a combination like AH or HA, you can follow the alphabetical order to choose a edge name. So now we are constructing a spanning tree for this graph. So right, we are going to construct a minimal spanning tree for this graph. And now what does step 1 will say? We have to collect all the edges with weights. So now you can see AB is a edge which having the weight is 4. So then AH, PH, HI, GH, GI, BC, CD, FG, DE, DF, and EF. So these are the different edges we are find from this particular graph. So now what your second step will say, we have to arrange all these edges which collected from a step 1 in ascending order. So by arranging all the elements in ascending order, you can see that. So here the less weight will comes first, and then the maximum weight will comes last. Okay, and what your step 3 will say, we have to pick one by one, right? We have to pick one by one edge, and we are going to put into a spanning tree. So we'll see that. So now step 3. So now you can see here it is like you have the first edge is GH. So we have to consider GH. So where it is? So it is, right? GH with a minimum, right? You have to consider this edge in your spanning tree. And then what will be the second is FG with a weight 2. Next, consider this edge. So now you can see here, FG is connected. Okay. And after that, you can see the third one is AB. Okay, with a weight 4. So now we are trying to connect A and B with weight 4. Okay, we are taken this edge is also consideration because it doesn't forming any cycle. Okay, and then we'll see the next edge is GI. Okay, with a weight 6. So now you consider GI. So where is GI? So here it is a GI. So you have to consider this edge also because it is also doesn't forming any cycle. And after that, we see in that C and D. So now where is C and D here? So now you can see C and D is here. Okay, we can consider because this is also not forming any cycle. So we consider this edge also. Okay, and then we have the next edge is HI. So now we have to find out where is HI first. Now you can see this is edge of HI. So when I'm taking this edge, so now I can see here the cycle is formed, right? So what do you mean by a spanning tree? You have to connect all the vertices, but it doesn't forming any cycle. So what your algorithm will say, you cannot choose that edge. Okay, we cannot choose that edge. So we have to remove that edge. Okay, so we have to remove this H because it's forming cycle. Okay, and then we have the next edge is AH. So here we can see this is AH. So if I connected this edge, it doesn't forming any cycle. So I consider this edge. Okay, so now you can see AH we consider. So you have to take this also from the list. And then the next is BC. So where is BC? So now you can see this is BC. So when you connected this edge, okay, so it doesn't forming any cycle. So we consider this also. So you can take this also consideration. And then we have DE. So now you can see, right, where is DE? So this is D and E. So when we connect this edge also, it doesn't forming any cycle. So you can consider that also. So now you consider this edge also. DE also we consider. Then we have EF. So now you can see where is EF. So this is your EF. So when I connect this, now it form a cycle. Okay. So when I connect this, it form a cycle. So I cannot consider this edge. Okay. I cannot consider this edge. And then I have next edge is BH. So you can see that B and H is this edge. Now you connected this, it form a cycle. So we cannot consider this edge also for constructing spanning tree. So we are not considering this edge. And then we have the last edge is DF. So where it is DF? So now you can see this is D and this is F. If I connected this, it form a cycle. So again, I cannot consider this edge also. So now you can see the list is empty. Okay, you can find, you can see that all the edges we are consider for constructing the minimal spanning tree. And here we are including some of the edges and some of the edges we remove from the list because it makes a cycle. So now you can see this is a spanning tree. Okay, this is a spanning tree. So now from A to B we have, and then from B to C we have an edge. From C to D we have an edge. And then from D to E we have an edge. And here in bottom, we can see from A to H we have an edge. And then H to G we have an edge. And then G to I we have an edge. And G to F we have an edge. Okay, and then we are not considering any other. So because already all the vertices are connected here. Now you can see all the vertices are connected here. So this is A, B, and this is H. And this one is G. And this is I. And this is C. This is D, E. And here it is F. So now you can see all the vertices are connected. Okay. And without forming any cycles. So this is a minimal spanning tree. So what is the minimum cost? So now you can add all. So here it is 4 plus 8, 12, 12 plus 8, 20, 20 plus 1, 21, 21 plus 6, 27, 27 plus 2, 28, and 28 plus 7 is 35, and then 35 plus 9. So this is the cost of this is 35 plus 9, it is 44. So this is a minimal spanning tree for the given undirected